In this lecture and the next, we'll talk about the isomorphism theorems, which are the focus of section 3.3 of Dummett and Foote. There are 4 isomorphism theorems. We'll talk about 2 in this lecture and 2 in the next lecture. So let me just jump in and tell you the first isomorphism theorem. This is the one about homomorphisms. So if you have a homomorphism phi from G to H, then the kernel of the homomorphism is a normal subgroup of G. We already know that. We actually have proved that in a previous lecture. We showed that the normal subgroups of G are exactly the ones that occur as the kernel of a homomorphism. But it tells you more. It tells you that G modulo the kernel, that this quotient group that is well defined because the kernel is normal, this quotient group is isomorphic to the image of the homomorphism. So let me say that in some sense, we also at least described why number 2 is true when we talked about the group structure on the set of fibers of a homomorphism. But maybe that's not so satisfying, and this is now like a good moment to practice some new things that we've seen about quotient groups, and we can give a much more concrete description of why this second statement is true. So, okay, we want to show that 2 groups are isomorphic. Let's write down an isomorphism between them. So we need a function that goes from G mod the kernel to the image. We want it to be a homomorphism, and we want it to be bijective. So let's call this phi hat. This is going to be a sort of common notation where you start with some homomorphism phi. Something involving the quotient often gets a hat over it, or a bar. And what it's going to do is take the left coset of the kernel containing A to phi of A. So what do we need to do to prove this theorem? We need to show first that this function is well defined, that it doesn't depend on a choice of coset representative for your coset A times the kernel of phi. Once we know this function is well defined, we need it to be a homomorphism. And then we want it to be an isomorphism, so we need it to be surjective and we need it to be injective. So first, let's say that show that this is well defined. So if you have a left coset A times the kernel of phi, what do the other elements of this left coset look like? They look like A times something in the kernel. So if B is equal to AK, then the left coset of the kernel containing A is the same as the left coset of the kernel containing B. So if you apply this map phi hat to A kernel phi or B kernel phi, that's the same coset. So it better be the case that phi of A is equal to phi of B. Otherwise, this map just doesn't make sense. So let's check. So what is phi of B? We want it to be phi of A. Well, that's phi of AK. And phi is a homomorphism. So that's phi of A times phi of K. But but K, the only thing we know about it is that it's in the kernel. So phi of K is the identity. So that means we get phi of A times the identity, which is just phi of A. So this finishes the proof that this function is well defined. So I'm going to pause and erase, and then we'll show that it is a homomorphism, that it's surjective, and that it's injective. Let's continue this proof of the big piece of the first isomorphism theorem, that G modulo the kernel of phi is isomorphic to the image of phi. We have this map, phi hat, that goes from G mod the kernel of phi to the image of phi that sends A times the kernel of phi to phi of A. So the left coset of the kernel containing A gets sent to phi of A. We've already seen that this map is well defined, that it doesn't depend on a choice of coset representative. So now we want to show that it's actually a homomorphism. So we're going to use the fact that phi is a homomorphism. So since phi A B equals phi A phi B, the thing that we want to understand is how phi hat AB times the kernel of phi is related to phi hat of A kernel times phi hat of B kernel. And now we can just write it down. I mean, this, by the definition of the map, is phi AB, which is phi A phi B, because it's a homomorphism, which is phi hat of A times the kernel, this first coset, and phi hat of the second coset. Okay, so that sort of trails off, but this is exactly what we need for phi hat to be a homomorphism. Now let's show that this phi bar, I should say phi bar instead of phi hat, that phi bar is injective. So let's suppose that this map sends two cosets to the same place. So what does that mean? That means phi A equals phi B. Okay, now what we need to use is this thing that we proved in an earlier lecture, that cosets of the kernel are fibers. So what does that mean concretely here? The coset A kernel phi is equal to the set of all of the things. So it's everything, let me say, x in G such that phi of x is equal to phi of A. So it's all the things that get sent by this map phi to the same place that A gets sent to. So what does that mean here? Well, we know phi of B is equal to phi of A. So that means, B is in this same coset, A times the kernel of phi, which means because two cosets that have non-trivial intersection are equal, A kernel phi equals B kernel phi. And that's exactly what we need for this map to be injective, this homomorphism to be injective. So now let's do the last part. Let's show that this is surjective. So what do we need? We need that any element in the target over here in image of phi gets mapped to by something in G mod kernel of phi. So any element of image of phi, what does it look like? Is equal to phi of A for some A in G. Okay, so what's the coset of the kernel of phi that gets mapped to phi of A? Well, phi hat of A kernel phi equals phi of A. So this map, this homomorphism is surjective. Now we're done. So I'm going to pause and erase, and then I'll talk, briefly mention some corollaries that I had written on the first whiteboard here, but didn't say anything about. And then I'll talk about some examples. Let me start by saying something about these corollaries of the first isomorphism theorem. So the first one is that our original homomorphism phi from G to H is injective if and only if the kernel of phi is the identity. Well, okay, the kernel of phi is a subgroup. It definitely contains the identity. And if it's not the identity, then there are two things that map to the identity, and your function's not injective. So phi injective implies the kernel of phi is the identity. And for the other direction, if the kernel of phi is the identity, then G mod the kernel is just isomorphic to G, which is the image of phi. So if G is isomorphic to the image of phi, then this map has to be injective. Okay, for the second piece, you just take the size of the two groups that are isomorphic, that the index of kernel of phi inside of G, that is the order of the quotient group G mod the kernel of phi. And since that group's isomorphic to the image of phi, they have the same size. Okay, so it sort of follows right away from the first isomorphism theorem. I want to talk about two examples that come from linear algebra. So we'll talk much more about abstract linear algebra later in the course when we talk about vector spaces and all sorts of other good stuff. But I know many of you have seen proof-based linear algebra before. So I want to mention now the rank nullity theorem, which is something you've probably seen. So if you think about the first isomorphism theorem applied to a linear transformation of vector spaces, you have phi from V to W, a linear transformation. And what does it tell you Well, V mod the kernel of phi is isomorphic to the image of phi. If you take dimension everywhere, which we'll talk about more, that says the dimension of V minus the dimension of the kernel is equal to the dimension of the image. But the dimension of the kernel and the dimension of the image have names. The dimension of the kernel is the nullity of phi, and the dimension of the image is the rank of phi. So what this is saying, if you just move this over to the other side, is that the dimension of V is the rank of phi plus the nullity of phi. Okay, one more example. Let's take this function phi from gln r to r star. Remember, r minus 0, which is a group under multiplication, where we take a matrix A to its determinant. So first thing to note, this is a homomorphism. Determinant of A times B is the determinant of A times the determinant of B. What's the kernel? Well, it's everything in gln that has determinant 1. And that has a name that's a group, the special linear group, SLNR. So it's the kernel of a homomorphism. So it's a normal subgroup. So we can take a quotient. And what is that quotient? Well, phi is surjective. Let's note that first. What does that mean? You take a real number, D, that's not 0, and you want to write down an n by n matrix of determinant D. Just take a diagonal matrix with a D in the upper left corner and 1s on the rest of the diagonal, and that'll work. So that means glnr mod SLNR, the kernel, is isomorphic to the image, but since this is surjective, that image is all of R star. So what is this saying? It's saying that gln mod SLN is isomorphic to R star.